experiment is free tutoring at scale. So, when one explanation can work for multiple students, I think that it is good and that I want to make as much impact as possible in a limited amount of time. The nice thing about this virtual platform is that the VOD gets recorded, and that when one explanation goes out, it can benefit basically anybody in the class. All right, so now let's continue. Sorry, I was just adjusting my settings a little bit. Okay, so integration by parts, right? How did we do this problem yesterday? dx, right? Now, what integration by parts is sort of screaming at you to do is that, the idea of integration by parts is that, okay, sometimes it's not very clear how to split it up, right? You could split it up into x and cosecant squared, or you could split it up into like x times cosecant as u and cosecant as dv, right? That's sort of the art. Integration by parts is sort of practice and an art more than an exact science. But for this particular one, if we let u is equal to x and dv is equal to cosecant squared x dx, then you find that du is equal to dx, and then v is equal to, I believe this is a standard integral, right? This is, I believe this is just minus cotan, if we look it up real quick. So as you prepare for this test, I was told that you don't get a equation sheet or trig identity sheet or anything, which is unfortunate. But you basically just have to keep in mind a list of the standard integrals and derivatives related to trig functions. I guess that's just part of life for the moment. But once you have this, right, this turns into minus x cotangent minus the integral of, or minus the negative integral, so it turns into a plus of cotangent. And I believe this should not be too bad, right? I think we looked at this last night. Integral of cotangent, I believe, is one of those standard integrals that you should have seen in one of your, in one of your textbook derivations. And yeah, looking it up real quick, it's ln of, I get to look it up because I don't need to know this stuff fresh, but you do. But I believe this is just ln sine of x, right? So this turns into minus minus x cotan of x, and then plus ln of sine of x, or whatever that is. And then you just have to plug in, yeah, that does kind of suck. Sorry. I guess you just need to know these things cotan isn't too bad, right? Let me show you how you would do cotan if you had to. You could always just write out cotan and tangent as, what is this, cosine over sine? And then this just turns into a u substitution, right? If this is cosine of x, sine of x dx, then you just let u is equal to sine of x. You let it be on the denominator because you want the du to pop out a cosine x and dx on the numerator, right? So this turns into this times this. So this just turns into integral of ln of u. This turns into 1 over u du, which just turns into ln of u, right? And then ln of u, well, okay, and then you just plug in the u over here, so it turns into ln of sine of x, and you have the idea. I think this one's no, it's not a definite integral, so I think you're basically done. All right? Feeling good so far, folks? Hopefully. How are you all feeling about this exam that you have? I only made contact with one of the students yesterday, and he told me that they felt maybe a little bit uneasy about it, but that most students felt not so bad. Calculus 2, a lot of your intro gen ed courses can really run the gamut in terms of difficulty. They can basically be as hard or as chill as the professor wants, right? So for this problem, another integration by parts, right? Problem 2. This one I think is very straightforward, right? This time, when you see an x on its own, or like a polynomial, that's not always, but like 90% of the time, it's screaming at you, because when you assign the polynomial to u, this is sort of like bumping down the complexity, so to speak. Does that make sense? It's bumping down the complexity because, so if dv is equal to sine x dx, and v is equal to minus cosine of x dx, the idea here is that, well, okay, when you do uv, that's these two things, not so bad, right? But when you do integral of v du, well, look, the x is gone. The polynomial sort of lost some complexity. That's the sort of, you have the theory of integration by parts, which is just the product rule in reverse, right? But in practice, you're always looking for how to do a split that lets you reduce the complexity. And yeah, at this point, it should be, any standard thing that anyone can solve at this point in your calculus careers. What about 3x? Where did it disappear to? Wouldn't you also integrate it with CSC? Yeah, you're right. The 3x I didn't care about so much. Like when you just have those constants of, when you just have those multiples in your integration, it ends up just popping out as a constant, right? So, okay, if you really wanted to do it carefully, this would look like cotan of 3x over a third, right? Like I said, this is a trade-off of speed versus precision. If we wanted to do things very carefully with all these little factors and whatnot being just right, we could do it that way. It'd just be a lot slower, right? But these things, when there's just a little scalar factor in front of the x, it's not so mysterious. It ends up just as a little bit of division. Yeah, we have to do those in the exam. Sure, I realize. But, what you gave me yesterday was a huge list of practice problems. And I think showing you all the concepts, in a compact form, I think is probably a little bit more important than, every single minor detail. Hopefully when you practice through these on your own, you would, go through all those things. But okay, I can pay more attention to little things like those factors if you really want me to. So yeah, when you integrate cotan of x, well, then there would be another factor of 1/3 popping out, right? So this would probably looking like probably a 9th. Over here, there was going to be a factor of a 1/3. Yeah, look, check my work. Make sure those little factors, but do you have an understanding of, like, frequently as you get a little higher in math, people are not quite as interested in these factors. Like, yeah, technically you need them there to be correct, but like in office hours, a professor or a TA isn't gonna nail down every single one of those factors, and except for the rare problems where they're actually important, right? In this one, they're important if they need to line up carefully for some cancellation later on. Here, they're not quite as much, right? So 14x sine of x, okay, the 14 isn't so important. Problem 3, right? Problem 3, I think, is a very interesting one because it showcases a particular technique that I think is very thematic. And I'm surprised that they only have one example of these because it pops up all the time in integration by parts. But if I remember correctly, what I'm going to do is I'm going to let this entire integral be equal to I, right? I didn't do this for the previous problems, but I'm doing it here for a very special reason that we'll see later on. So, okay, let's go ahead and try to do our usual u-dv pairs. And then dv is equal to cosine of 4x dx. So then du is equal to minus e to the minus x dx. And v is equal to, what is this going to turn into? A minus, nope, just a regular sine, no minus. Sine of 4x 1/4. Right? So then this turns into u to the minus x, a quarter, sine of 4x, minus a negative. So I guess that turns into a positive. E to the minus x. Okay, so the quarter pops out here, sine of 4x. Okay, let's pause for a moment. Okay, I guess we've made some progress, but like, oh gosh, this is kind of nasty, right? E to the minus x, sine to the 4x isn't really less complicated than e to the minus x cosine 4x, right? All we've done is swap out a cosine for a sine. It almost feels like we've made no progress. And normally I would agree with you. This would, if this was another type of problem and we just switched out one thing for another, I'd be like, oh man, maybe we're going in circles. But for this particular problem, going in circles is quite the point. Going in circles is exactly what you want. Because when we integrate this out again, a second time, right, we're going to use integration by parts once more. So e to the minus x, dv is equal to sine 4x dx. And this turns into du is equal to minus e to the minus x dx. V is equal to, I guess this time it's minus 1/4 cosine of 4x, right? Hopefully that work is right. But now we're going to plug this in. Okay, e to the minus x. And remember, this whole thing, I was equal to this whole thing, and I is equal to this whole thing. Sine of 4x, what is this, plus a quarter. Again, I'm trying to go a little bit fast to show the concepts here, but e to the minus x, so the next one, negative 1/4 e to the minus x, cosine of 4x, minus Okay, gosh, this is so many signs. Minus, I think this is a quarter integral of e to the minus x. Right, it gets nasty. This is just part of the course. Calculus 2 is a bit of a slog. But hopefully I did this right. Minus a negative of a negative is overall a negative. Fourth e to the minus x cosine 4x, right? Okay, I think I did that right. Was this a definite integral? Yeah, it was from 0 to infinity, right? So what we'll notice is that if we evaluate the definite integral from, I think, 0 to infinity, I believe this turns out to be a 0, right? And then I believe this one turns out to be, I'm going to evaluate it a little bit ahead of time because I know what's going on from 0 to infinity. This also gets evaluated from 0 to infinity. I believe this turns into positive 1/16 minus 1/4. Sorry. Excuse me. Minus 1/16. Minus 1/16 integral e to the minus x cosine 4x dx from 0 to infinity, right? So do we see the trick here, folks? Do we see the trick here? This is exactly the same integral that we started with, right? This is e to the minus x cosine 4x dx. And now we've seen the exact same thing here again. When I was going through calculus, I never heard of a name for this trick. But recently I heard one from, I think, a Russian student, or maybe it was a German student, that in their country they call this the Phoenix integral, because you see the exact same version of the integral that you started with, only a little bit smaller, right? It's sort of like a smaller integral rising from the ashes, so to speak. But the idea is we can solve this just like it was algebra, because we can move this over here. This is, at this point, it's basically the integral is equal to 1/16. I is equal to 1/16 minus 1/16 I. So this turns into 7/16 I is equal to 1/16. And then I is just equal to, I think this is 1/17 is what I got. Does that make sense? This is a very common trick you see in these integrals, where you can never bump the complexity away totally, but you can get something like, you can get something that looks a lot like the integral you started with, just being multiplied by some factor, like 1/16. And because this, it feels a little bit confusing, perhaps. The first time I saw it, it didn't feel like that was allowed. But really, that's totally fine, right? This is basically just, once you realize that you can rewrite the integral as just I, this is basically just algebra. This is basically just middle school algebra, right? We feeling good about that one? Hopefully we can just move on. So for this one over here, cosine of 7x dx, right? The idea here is that, okay, we have a habit of assigning the polynomial factor to be u, because we typically like to bump down the complexity. Now, keep in mind that while this is a great rule of thumb that I'd say works 90% of the time, there is about 10% of the time when it doesn't work. And unfortunately, I don't have an example on hand, because I don't see any of those examples on this homework set. But it's something that'll get you by most of the time, but every now and then when something's tricky, you gotta watch out. That's just how it is, right? So this problem isn't very interesting. It's just very, very tedious, was what I found, right? So the issue here is that you're basically gonna have to do integration by parts a whopping 3 times, because we need to keep bumping the complexity of this polynomial down once each time. And, honestly, that's just a pain in the butt, right? So what does this turn into? This turns into x cubed 1/7 sine of 7x. I believe it's an indefinite integral, so we don't need... Oh, by the way, for the indefinite integrals that we had earlier, you obviously have to add a c to them, right? Whatever this was, you have to add c to it. I didn't do this all the way through, but whatever you get at the end, you have to add c, right? Because it's indefinite. How are we feeling, folks, so far? Is a style reasonably productive? Do you feel like we can just go through these problems and just show you a lot of variety, give you some background for your exam preparation? My hope is that my hope is that you all are reasonably comfortable with the basics. You just need a lot of practice. And maybe it's a situation right now where it's a little bit hard to practice on your own because you just don't have that much familiarity yet. But this problem isn't too crazy or anything. Like I said, you multiply through, I guess that's 3/7, and this turns into x squared sine of 7x. And what you have is something pretty similar to your initial integral, except for instead of x cubed, it's x squared, which means that you've made a little bit of progress in bumping down the complexity of this integral. So you would just repeat this process like 2 more times, right? You would repeat the process with u is equal to x squared, dv is equal to sine of 7x dx, and go from there. So you would eventually come across an integral that would probably look like x cosine of 7x. And then after that, after doing some more integration by parts, you would probably come across something that just looks like sine of 7x. So this problem is a little bit tedious, but it's definitely very mechanical. Some of the classmates don't have an account, but are very grateful. Yeah, sure. Of course, we hope you stay. If you know other classmates, if you have other friends who are perhaps struggling or could do with some extra practice, please go ahead and invite them too. The concept of this experiment is sort of teaching at scale. When an explanation can benefit 1 student, I would like it to benefit maybe 10 students, because one of the limiting factors from teaching is not being able to communicate with so many people at once, right? And a VOD, a recorded video of this, will be available on my Twitch channel for, I believe, at least a week or 2. Where did the 3/7 come from? Well, the 3 came from over here when we did the when we took the derivative of x cubed, and the 1/7 came from integrating cosine of 7x, right? So when you do your VDU pair, when you integrate VDU, well, you have to multiply these 2 together, right? So you get a 3 and a 3/7 popping out in front. And please, folks, go ahead and, we have a Discord if you want to ask questions. You can also just comment by making a free Twitch account. I believe it should be free. I mean, yeah, Twitch is definitely free, right? But yeah, like I said, I'm available in the calculus channel of the Discord if anybody wants to ask questions live. I found that can be very helpful in the past as well. That way you don't have to type things when you're confused. But yeah, I hope this format is reasonably productive, and we'll keep going. So question 10 is asking about from 0 to 1. Just didn't realize where the 3 got pulled with it. Yeah. The 3 was just from, it popped out from taking a derivative, right? So this is, hopefully the idea is that if you have someone guiding you, that studying like this can be a little bit more productive than if you were tackling things entirely on your own. That's the hope, right? That's the hope. Okay, so here's one where my initial try with this problem was actually unfruitful. What I mean by this is my very first thought was, let's do u substitution, right? So if we let u substitution u is equal to x plus 1, I was hoping that du is equal to just dx, but the issue is that if you sub this in, there's still a big fat x lying around here that it's hard to know what to do with. It's actually, now thinking about it, there might have been a way to make this work, but I found a nicer way of doing this with integration by parts, right? So if you do integration by parts, the choice for this one, again, I'm trying to let x be equal to the polynomial part be our u, and then the slightly nastier part would be dv is equal to 1 over root of x plus 1 dx. Could you also use trig sub with it to make it easier to solve? Yeah, I was thinking about trig sub a little bit, and I think it's plausible, right? You could probably sub this one in for tan squared of u, but as of right now, because this section was suggesting integration by parts, I'll stick with integration by parts for now. I think that would work just fine. This one seems like a reasonable candidate for a trig sub, because then tan squared u plus 1 turns into secant squared, right? And that disappears nicely. So, okay, so if du is equal to dx, then v is equal to, oh, what the heck is this? 2 rad x plus 1, I believe. And, well, this starts to look pretty promising, right? Because then u dv just looks like 2x root x plus 1. And then this becomes the integral of 2 root x plus 1 dx. And at this point, this should be something that I hope you all know how to do, right? Just a lone radical standing by itself, basically, is not going to be too hard to breach, because it just gets bumped up to a 3/2, right? So this turns into 2, and then I guess from anti-chain rule, you get 2 and a 2/3 here. So this looks something like this. It's not a hard problem, so I guess I'll just write this one out, right? And I think you have to evaluate this from 0 to 1. And if I'm not mistaken, I think I got something that looked like... you also have to evaluate this from 0 to 1, which just turns into a, I think, 2 root 2. Minus 4/3 times, what is this? 2 to the 3, right? 2 to the 3/2. Minus, I guess, 4/3. Yeah, something like that. Anyways, at this point, it's all just plugging it in carefully. I don't want to spend too much time on it. Could I scroll back up? Sure, sorry. When I'm focusing on this stuff, it's hard to address things too fast while live. So if you have requests like that, it might be more helpful to... like, I also don't know how far you want me to scroll up, right? Do you want to look at the previous problem? Or are you trying to look at something over here? Anyways, if you have requests like that, it might be more beneficial to just hop onto Discord or get into a voice call so you can tell me what you want to see live. But yeah, at this point, yeah, I forget. You just need to plug that in. It turns into 2 3/2 minus 4/3. Yeah, it looks more or less right. Just do it more carefully on a test, right? But what I'm trying to get at here is not get every single factor of 2 right, because that's just going to take too long. What we have to do here is go through a lot of problems to build comfort with these concepts. 7x plus 8 dx. Yeah, I mean, what do you want to see here? Is there anything in particular that was problematic? The gist of these integration by parts problems basically boils down to your selection of u and v. And once you have those down, usually it's not too bad. Anyways, for this problem over here, this one I think was actually one of the tougher ones in my mind, because it's really not very clear. It was not very clear to me the best way to address this, right? And let's see, I did get it somehow, but it was not very pretty, I don't think. U is equal to x plus 8. Okay. Yeah, so what did I do for this problem? U is equal to y. Gosh, I'm trying to remember. I had my notes over here, but unfortunately my handwriting is terrible and I can't even read what I did. So this was number 11, right? I think this one I probably just did du is equal, does this look right? Du is equal to this, 7x plus 8. Du is equal to square root of 7x plus 8. Or sorry, this is just u is equal to 7 plus 6. Du is equal to 1/2 7x plus 8 to the minus 1/2 times, I guess there's a factor of 7 here, so this turns into 7/2, right? Dx. And then, okay, so if we want to isolate this, this becomes 2/7 7x plus 8 to the minus 1/2 du is equal to dx. And this over here itself is just a factor of this over here is just a factor of u itself. So this just becomes 2/7, I think, u du is equal to dx, right? So maybe I'm being barbaric here, but I don't think this is even necessarily integration by parts. At least not in the first step anyways. But okay, we have 1/2 2/7 u du, and then we replace, and then that just looks like e to the u du, right? Because, okay, the e, this is e to the u, and then dx is all this stuff. Which one is v? Right now I'm doing u substitution rather than integration by parts. We're about to use the integration by parts in just a moment, right? But the 2/7 came from the chain rule, right? This is all chain rule. The 1/2, so, right, this is equal to 7x plus 8 to the 1/2. The 1/2 gets bumped down by the chain rule. That's where the, over 2 part comes from. And then the 7 comes from the chain rule later on. From the 7 out here, it pops out. So I think there's still quite a few questions about chain rule, which kind of indicates a little bit of discomfort with that concept. That's something I think you've got to get really solid on. That's not something I can just, imprint on your brain, right? If you see factors like this, more often than not, it's going to be some consequence of chain rule. And you just got to go through for yourself and verify, or maybe I even made a mistake. Maybe you got to correct me. But for the most part, it's not terribly interesting, except for the very rare occurrences where you rely on them to cancel out. But at this point is when you want to do integration by parts, right? All that was, the issue here was that, we have this complicated rad 7x plus 8 on its own, and we needed to reformat it in such a way that, the issue here is that if you try to integrate it, right? If you try to integrate this, well, the derivative of e to root 7x plus 8 is itself. So you basically need to have some other terms here that sort of soak up the chain rule effect, so to speak. Which is why we went through all this trouble to rewrite it in a different form when there's an u out here, because this we can at least work with, right? So, okay, because we're already using the variable named u, instead, now let's do like a y, maybe let's call this a y dz pair, right? Instead of u dv, let's use y dz just to not reuse things that we're already, just to not reuse variables that we've already called dibs on. So this turns into dy is equal to du, and z is just equal to e to the u, right? And at this point, it really shouldn't look so bad. So I think this 1/7 cancels out. Right, so so 1/2 to 2, 1/7. So what does this look like at this point? This looks like e to the u minus the integral of e to the u du, right? And this really shouldn't be so bad at this point. Right? Integral of e to the u is just e to the u itself. So this looks like e to u minus this plus c, right? 1/7. And for problems like this where you did some kind of substitution, you do have to remember to plug in, because u is just something that you yourself defined, right? It's kind of meaningless to the context of the original problem. You got to always remember to go back and plug in u is equal to, in this case, square root of 7x plus 8. Right, so this turns into square root of 7x plus 8, e to the 7x plus 8, minus e to the 7x plus 8, something like that, right? Something like that. I think we have a 1/7 out here. Yeah, all right, folks, let's take a quick pause here. I just wanted to get some feedback here. Do you feel like this kind of structure is beneficial right now? Am I making sense? Is the format hard to follow? Do we have anyone that wants to get onto Discord and sort of ask questions on behalf of the class? How do you feel about this right now? I'm good to keep going. I just wanted to pause and get some feedback so I'm not droning on if there's some systemic issue. Could follow along okay? Well, I'm happy to hear. Okie dokie. Any feedback from me so far? Anything that, by the way, how big is this class? Is this like a massive lecture hall, or is this like a course where a single grad student gets like 30 students? These calculus classes really run the gamut in terms of teaching style and whatnot. Okay, so it's not a huge class, right? X squared plus 13. Oh, wow, that's cool. So if we have like 10 people in here, that's probably like half the class, huh? Very cool. Is this just like a very small college, or is this just a situation where there's a lot of Calc 2 classes and they're broken up to a lot of different sections? 12? No. Community college. Gotcha. Let's see. X squared plus 13. Yeah. Well, I'm happy to have you all along. X squared, square root of x squared plus 13. Always happy to provide help. Okay. Yeah, this problem was another one that was just a huge pain in the butt. Incredibly obnoxious. Now, this one's a little bit thematic, though. This one, I think this one is pretty good, because if I remember correctly, there was actually a very clever trick in terms of getting things to work out right. 2 buildings, so a small one compared to other campuses. Different campus, ours just not that big. Okay, cool. I'm curious, are things in person right now, or are they remote? I'm assuming that this is the US, but, you know, and of course, if you don't want to tell me, you don't have to. This problem, however, is pretty good because I'd say it's thematic. When I say something is thematic, I'm saying that it demonstrates a big concept or like a very important counterexample to a general process that we've learned before. And you know how I said that most of the time you're letting u be equal to the x squared part? That's not always what you want to do. In this particular case, in this particular problem, I tried it out a couple different ways. And if you just try out letting u is equal to x squared and dv is equal to this thing on the bottom, I couldn't get that to work out so nicely. Maybe someone else can, but I took a quick glance at it and it seemed miserable. So in this particular case, I'm doing this. Okay, I shouldn't call it clever, but I'm using, I think, a slightly different breakdown than usual, where I'm letting u is equal to x and dv is equal to x out of square root of x squared plus 13 dx. So I'll talk about the motivation in a second, but can you see why this is allowed? Like, there's no issue with it, right? The rule for u and dv is just that together they have to multiply up to be the original integral. And although we haven't done it this way in the past, you totally are allowed to split up the x over here and the x over there, right? This shouldn't be too mysterious, but the motivation is because x squared plus 13 and this x over here form a really nice u du pairing. I guess I should call it like maybe a y dy pairing because u is already being used. But the point here is that this forms a integral that we know nicely how to do using just u substitution. Right? This is just plain old u substitution. So, okay, so if du is equal to x, and I want to evaluate this integral off to the side, right? This integral is going to be, v is equal to x over x squared plus 13 dx, right? If we use something like u substitution, we'll call it y instead. So if y is equal to x squared plus 13, then dy is equal to 2x dx, right? So this integral becomes 1/2 dy over square root of square root of y. And you definitely know how to do this, right? You definitely should know how to do this. This is just I guess we have another factor of 1/2 popping out, but this turns into, what is this, y to the 1/2? No, excuse me, it should be a factor of 2 when you, right? So you go 1/2, yeah, it gets back to what we had in the start, right? So then these two cancels out, so this just turns into the square root of x squared plus 13. So our v here is the square root of x squared plus 13. This maybe is one of the harder, more subtle things that we've seen so far, but do you all understand why I did it this way? Do you understand why I did it this way? It's because, again, just to repeat the big concept of this problem, it's that splitting it up in sort of a motivated way. And I got this a little bit by trial and error, a little bit by intuition, but splitting it up this way lets you have, oh, sorry, I see what you're saying. This should just be dx. Good catch, good catch. But splitting it up this way lets you have something really nice and simple over here, right? So u and v is not bad at all. And then du and dv is also not bad at all, right? You can totally integrate this thing on its own without too much trouble, right? Okay, okay, it's not great, but I got this using a tangent, a trig substitution. But this is the idea that I had, and maybe there's an easier way up there, but this is how I did it. Right? And to give you an idea of how to integrate, so what does this turn into? X square root of x squared plus 13 minus the integral of square root of x squared plus 13 dx. And the way that I did this was trig substitution. So I basically said, okay, we want to let x squared be equal to 13 tangent squared of 13 tangent squared of z, right? 13 times tangent squared of z in order to make use of one of the tangent identities. So then, okay, x is equal to rad 13 tan of z And then dx is equal to rad 13 secant squared of z. And we'll go over a lot more problems like these in the second part of the set. But this starts to look like, okay, what does this start to look like? Integral of rad 13 secant squared of z divided by, okay, so this turns into 13 times tan squared of z plus 1, right? And this is just secant squared of z. So I'll write this over here, x squared plus 13. So this is secant squared. So let's just simplify this a little bit. The rad 13s cancel out, I believe. And I believe, this secant squared just turns into a secant because of the square root. So we get some cancellation that looks like this. dz. Y square root of 13. The square root of 13 comes from, again, from a chain rule. So we chose x squared equal to 13 tan squared of z because we want to make use of the identity that tan squared of z plus 1 is equal to secant squared of z, right? And if we multiply both sides by 13, this sort of turns into tan squared z plus 13 is equal to secant squared, or I guess 13 secant squared of z, right? So when we're looking at this thing over here, we're really trying to get this to line up with 13 tan z squared plus 13, which is basically why we chose x squared is equal to 13 tan squared z. So then x is just equal to square root of 13 tan z. The tan was basically the inspired part. This is what trig substitution integrals are, right? When you see an x squared plus a 13, or something that looks like this, that should be, you should get to the point where your intuition is just screaming tangent, right? Because this is the substitution. When you see x squared plus 13, the idea here is that, okay, the square root of a sum of two terms is really hard to deal with. But if we can convert this from, if we can convert this x squared to something that looks like tangent squared, right? Then we can replace this with a secant. And then a secant, because it's only one term, is actually really easy to square root. The square root of secant squared is obviously just secant, right? This is the whole idea behind trig substitution, is that when you see something that looks like x squared plus some constant, you can get rid of this. You can make this simpler into a secant if you massage it, right? So yeah, I'll let you maybe look through. I'm going to do a lot of examples like these, so hopefully the point should become like bolted into your head after a couple examples. But right now I'll move on for the time being. This turns into secant z dz. This should be some secant z dz should be some relatively. Oops, did I hold on a sec. I think I dropped something over here. I think I might have made a slight error either in my work or in my notes, because let's just do a quick sanity check here, right? So x squared plus 13. Yeah, I don't know why I divided. Sorry, I was getting this mixed up with another problem where I was dividing. I should be multiplying, right? There's no division in this problem. So this looks like rad 13. X squared plus 13, the square root of that, turns into sorry about this, folks. Let me just quickly write this out again. This turns into 13 tan squared z plus 13. And then that's just subbing in for square root of x squared plus 13. And then dx turns into rad 13 secant squared of z. And then this is all dz, right? So if you just look at this, the 13 and rad 13 and the rad 13 just pop out to be a normal 13. And then this turns into square root of tan squared z plus 1 times secant squared of z dz, right? And then the point should emerge because tan squared of z plus 1 is just secant squared. So this turns into the square root of secant squared, which is just a secant. So this turns into 13 times secant of z times secant squared of z dz. So what does this look like? This looks like 13 secant cubed z dz. See what I'm getting at here, folks? Shouldn't be too bad, right? Shouldn't be too bad. At this point, you should use whatever methods you typically like to oh right, I remember this problem was really annoying because I couldn't seem to figure it out in any way other than relying on this really obnoxious reduction formula. So this problem, I honestly don't know if the teacher intended for this problem to be as hard as it was, because I don't see any way to do this with like super basic means. Maybe there's a clever way to do this integration by parts, but I mean, we already used integration by parts up here, right? So I wouldn't worry about this problem too much because, like I said, there's this really strange thing called the reduction formula that is like a silver bullet for this kind of integral. But I think that the problem is instructive enough if you can just get it to this point right here. Are you familiar with the reduction formula? Because that's not something I ever learned when I took this calc class. Are you familiar with a reduction formula? You are. Wow, that's fascinating. I had literally never heard of it throughout my entire math degree. Okay, well then let's look up the secant reduction formula. Okay. So secant of, it looks to me like, if I just look it up on Google, it's saying that this integral of secant nx dx is equal to, wow, why is this got to be so complicated? Why does this have to be so complicated? N minus 2. Oh, sorry, I have to find the correct one. Have it written down on an index, but it's for sine and cosine. Yeah, I just never had seen this reduction formula before, right? But looking it up, it looks like, okay, I guess you can prove this by integration by parts. I've never actually done it myself. But what does this look like? Secant n minus 2 tan x n minus 1 plus the n minus 2 over n minus 1 integral of secant n minus 2 x dx, right? And I think at this point it should all be stuff that hopefully you know how to do, right? So for us, n is equal to 3. So this turns into secant of, what is this? Secant the first power of x tan x divided by 2 plus, I think this is 1/2 secant x dx, right? And the integral of secant should, so this will turn into just the integral of secant x dx. And I believe this should be a very standard integral that you can look up somewhere. But yeah, it's honestly a bit of a pain, and I think more trouble than it's worth. But yeah. By the way, I'm looking at how to actually prove the reduction formula, and it looks to me like you have to, I'm getting a hint that you have to integrate by parts with u being equal to secant n minus x, and dv is equal to secant squared dx. Interesting. So basically they're saying to prove that this formula is what it has got to be, you basically use u is equal to secant n minus 2 x, and dv is equal to secant squared x dx. So you can sort of see how you're taking n minus 2 factors of secant over here, and you're taking 2 factors of secant over there, right? So yeah, okay. That's seems to be, I guess this problem is technically solvable by stuff that you've seen. I just, it looks like it sucks. But, you know, at this point, if you just use the reduction formula, you should be able to get it in terms of an elementary integral, which is just the last thing you have to solve is the integral of secant x dx, which I'm pretty sure your teacher will have done for you, right? Integral of secant of x should just be, yeah, it's some nasty thing that looks like ln of sine plus cosine minus ln of cosine minus sine. Yeah. I don't envy you all for having to, you know, have to be fresh on so many topics, but you know, it's just something everyone's got to go through at some point in their math careers, right? So then the last problem in this section is the integral of ln of 2x squared, right? And there's probably different ways to do this. I'm sure that there's different ways to do this. I think for me, I set I did integration by parts with, yeah, I did integration by parts using u is equal to ln of 2x and dv is equal to ln of 2x dx. This worked okay. It was a little bit messier than it needed to be. And then what I realized that if you do, so this is not too common in integration by parts, but it does happen every now and then where you just let u be equal to basically the entire argument. We call it the integrand, and then just dv is equal to dx. And every now and then this works out really cleanly. So that's what I'm saying about integration by parts, right? Sometimes it's more of an art than a science, and you just have to try different things out and see what works. But okay, so if we do take the integral derivative of this turns into ln of 2x, right? And then you have to do chain rule, so this turns into 1 over 2x, and then chain rule again to fact the power of 2, right? So the 2's cancel out, and this looks something like 2 over x ln of 2x maybe. And obviously v is just equal to x, right? And the reason we did it this way is because, well, okay, the uv pair is, you know, never too bad. X ln 2x squared minus the integral of 2 ln of 2x over x times x. Of course, there was a dx in here. I just didn't write it out. Right? The reason we chose, the reason why this works out cleanly is because the x and this x cancel out perfectly, and all that's left is a relatively elementary integral, which is just the ln of something, which is not bad at all. I'll let you look up in your textbook how to do this, but I believe this just turns out to be what the ln of x is basically x ln of x minus x, right? So the integral of ln of 2x becomes, well, you just have to do that with 2x everywhere, which means an extra chain rule. So it's to 1/2 ln of 2x times 2x minus 1/2 times 2x. So yeah, this shouldn't be so bad, right? This shouldn't be so bad at all. Okay, you get a little bit of cancellation, but you get the idea. So that's all the integration by parts problems that I looked at last night. How are we feeling, folks? Does this feel all right? What's your comfort level? What I typically ask students is on a comfort level of like 0 to 10, where 0 is total panic and 10 is feeling pretty good about these problems. How do you feel on a scale of 0 to 10? (6.5). Okay, that's not bad. I think a 6.5 a couple of days out from an exam is not terrible. About an 8.5. Good. Okay. I'll take it for faith that there are other students here as well who just haven't made an account. Hi, Yuli. X is equal to 0.5 e to the u. Did I make a mistake or something? Is this a simplification? What do you mean? I tried and I think it is equivalent to your method. Twitch just cut off my first message. Oh, I see. Okay, so I'm working here with a different Calc 2 class that I, someone messaged me on Reddit and asked for a little bit of help, and I, decided to get the class together to do a little bit of review before the midterm. I have some help for the class that's seeing this for the first time. I have some other math hobbyists in my chat, like Yuli the Mooly, who sometimes pop in and offer suggestions and alternate methods. But yeah, are we feeling good? Are we ready to move on to the next part? Hi, folks. Hope you all get along well. Yeah. Do we want to do some trig integrals? Or do you want to take a quick break, let your brain rest a little bit, get a drink of water? How are you feeling? Feeling good? All right. Should we just keep going for now? Should we just keep going? There's a lot of different problems. The class set a small break? Sure, okay. Yeah, okay. Let's take a 5-minute break. Let's get back at, what is this, 6:05 Eastern? So right now is like 6 o'clock Eastern time. Let's take a 5-minute break, okay? Sounds good. I hope you're all enjoying the format, by the way. I hope it's reasonably educational and efficient. As always, any feedback is very welcome. Okie dokie. I just got a quick drink of water. I'm back. We're still going to honor the 5-minute break, but if anyone has any questions or, any suggestions or not, now would be a good time for a little bit of discussion. Hope you all are finding the format reasonably educational, by the way. You never really learned trig sub properly in your major? You just sort of saw people using it all the time and read it? Yeah, sure. Ask a question 1 on the calc assignment. Go for it. Is Medical Marvel from the other calculus class? Is there some sort of inverse trig sub? Yeah. So they're not on the inverse trig parts yet. So we're not going to see anything too nasty from the arc cosine, arcsine, or arctan. But there is the very frequent trig subs that you see is when you have something like some constant plus x squared, turning this into a tan squared. You want to basically turn this into a c tan squared u. So basically you let x squared is equal to c tan squared u, because you want to take advantage of tan squared plus 1 is equal to secant squared. Right? And the idea is that if you can replace this with a secant, well, then the secant squared, then the square root applies to it, and then you just get pop out with like a secant with some like root c in front. And that's the trick, right? Class said that this is helping us a lot. Well, that's wonderful. I'm very happy to, I'm very happy that's the case. And again, if you have a class of 20 people or so, invite everyone that you know, because the goal here is to help as many people as I can in a fixed amount of time. Hi, everybody. Hope you're doing well. But yeah, Medical Marvel, please go ahead, ask a question. I started a little bit early because there was this new class doing Calc 2 stuff that I wanted to give some special attention to. But, we're getting to the general hours that I usually hold these, evening sessions on. So anyone that wants to ask a question is welcome to. And in between, I'll just be going through this list of big problems. So yeah, Medical Marvel, please go ahead, ask. Okay, I think we're getting to the end of our break period. So I hope you all are ready to crunch some more calculus. Yes, ready. Okie dokie. And folks, for people listening, you if you want to be able to ask questions yourself, you don't have to go through an intermediary. Just make a Twitch account. It shouldn't be too hard. Shouldn't cost you anything either. But yeah, let's get to some trig integrals, folks. So I believe this is question 19 from the list that I was given. So we're looking at sine cubed of... Wait, we already did this one, right? Let's just do it again real quick, right? It's not bad. The trick here is to split it up into sine squared of 3x times sine of 3x. And then you turn this part into 1 minus cosine squared of 3x times sine of 3x, right? Because then this turns into sine of 3x, which you know how to do. And this turns into cosine squared of 3x, sine of 3x, dx. And the idea here is that if you just let, when you have a cosine to a power, and then you have a sine by itself, this is basically screaming that you should be using u substitution, right? Because if you use u is equal to cosine 3x, du is equal to minus 3 sine of 3x, right? You can always manipulate these, constants around as need be, but this is basically saying minus 1/3 du is equal to sine of 3x dx, right? So just to give you a quick idea, this part of the integral, the sort of nastier part, turns into minus 1/3, or I guess it's minus 1/3. What is this? Basically u squared du, right? And you should all know how to do this at this point. This just turns into, u cubed over 3. Right? Hopefully not so bad. Hopefully not so bad. So that was the quick gist of that problem. 2 cosine cubed of 3x dx, problem 20, is basically the exact same idea, right? There's like really great symmetry between sine and cosine. So if you know how to do this problem with, okay, so the 2 doesn't really matter, right? This is just a constant that pops right out of the integral. But no, please, the whole point of this is to help people at scale and juggle some questions around. But I'll address this question and I'll get to your question right afterwards, Medical Marvel. It's more interesting for me when I have a lot of subjects to juggle between. So I'll happy to take a look. I should probably schedule, when is the York assignment due, by the way? But anyways, the idea here is that you should split this into cosine squared of 3x and cosine of 3x, right? And it's the exact same idea, This, instead of cosine squared, this turns into 1 minus sine squared of 3x times cosine 3x. Integral signs. So then this turns into cosine 3x, which you all should know how to do, minus sine squared of 3x cosine 3x dx, right? The dx was invisible. I just didn't bother writing it. But okay, here we let u be equal to sine of 3x and du be equal to cosine of 3x. And there needs to be a 3 because of the chain rule, right? And you can see how cleanly this is going to let us integrate this thing by using u substitution. So I'm going to take a quick look at Medical Marvel's problem from a different homework set. This should take less than 2 minutes, while I let the rest of you take a breather and maybe come up with some questions or whatnot. So you're asking, why are all the terms divided by theta to the 4th for this fraction? They're just trying to compute the limit. That's all that's happening, right? Can we use the trig identity even if it's 3x? Sure. I mean, what is 3x, right? Like, if you may as well just let 3x be equal to y, right? Yeah, you can totally use a trig identity. You know, sine squared plus cosine squared. You know, you can do sine squared of 10x plus cosine squared of 10x is still equal to 1, right? Because 10x is really just some other variable that you can think of as like y. But yeah, you see that what I'm getting at with your fraction problem? If you have something that's like x to the 4th plus x to the 3rd plus x to the, squared or whatnot, and then you have like, or I don't know, something out here, and then you have like, x to the 4th plus x squared plus cosine of x or something. I mean, if you take the limit as it goes to infinity, right, you can just eyeball it and see like the biggest terms. This is a 2 and this is a 1, so the limit is 2. But if you want to do it a little more carefully, then the common way to do it is to like divide everything by x to the 4th. Divide everything by x to the 4th, right? That's all. Yeah. Anyways, back to the calculus problems here. Okay, 21 starts to get into well, I don't even think it's really that hard. Cosine 4 of 3x dx, right? So before, when we had to a cubed power, it worked really nicely because you could use the sine squared cosine squared identity and have exactly 1 power left over for your for your u substitutions du, right? We don't get that quite as nicely when we have something to the 4th power, unfortunately. But all is not lost. All is not lost. We definitely can still do something about it. Right? There's got to be like an easier way, though. Yeah, the way that I came up with was not particularly nice. It's just, it's just what I came up with. So what I thought to myself was, okay, even though it's not going to be as nice as before, we're still going to split this up into cosine 3x and cosine squared of 3x. Right? And then we're going to turn this part into 1 minus sine squared of 3x. So what this is going to look like, so the 3 pops right out. So this is going to look like cosine squared of 3x minus cosine squared 3x times sine squared of 3x. And what we're trying to exploit here is the double angle formula, right? We had, remember, the double angle formula is basically saying sine of 2x is equal to 2 sine of x cosine of x, right? So this is basically saying, if you look at it this way, cosine of 3x times sine of 3x, I should write it the other way, you'll get the idea. Sine of 3x cosine of 3x, this has got to be equal to 1/2 times sine of 6x. You see what I'm saying? You see what I'm saying? So cosine squared of 3x, I think, is not too bad. I think this should be doable through UDU pairs or something. I'll address that in a second. But this part is the more interesting part of the problem, right? Cosine squared 3x, sine squared 3x, because this just turns into 1/2 sine squared of 6x dx. You see that? Yeah, I can take a look at number 2 right afterwards. Cosine 3x minus 1/2 sine squared 6x. And now it's just a question of how do you integrate a cosine squared, or how do you integrate a sine squared? Because that's almost exactly the same concept, right? And maybe there's a cleaner way to do it, but the way that I came up with, or the way that when I say came up with, I knew how to do all this stuff like 7 years ago when I was learning it. But I'm rusty, right? So sometimes I have to come up with stuff again. But I did this with UDV, with integration by parts, where du is equal to 2 cosine of 3x sine of 3x times, I guess, a 3? I guess there's a negative sign that pops out here because of cosine going to sine. And then v is just equal to x. Right? So then hold on. Did I make an error here? Did I make an error? Here it is. This is just the trick here is that this is just a double angle formula again. So this turns into a -3 sine of 6x, right? This isn't so bad. This is just du is equal to -3 sine of 6x. So then what does this turn into? Okay, uv is just cosine squared of 3x times x minus the integral of, what is this, -3 sine of 6x times x. And at this point, just remember from the initial part of the session, this is just some simple integration by parts at this point. Can we write cosine squared divided by sine? Where are you getting the division? Is that to get another cosine squared of 6x, right? So anyways, this is the idea here, is that when we had cosine squared, we can take it, the derivative. The du becomes a cosine times a sine, which is like prime real estate for us to use the double angle formula to convert this just to a sine on its own, right? And at this point, okay, uv minus what is it, v du, and this is something that you should be able to know how to integrate from the first part of the homework assignment, from the first part of the assignment, right? And then over here, the sine squared of 6x is pretty much the exact same thing, right? We integrated cosine squared of 3x to integrate sine squared of 6x. Just let u is equal to sine squared of 6x. So then du becomes 2 sine 6x times cosine 6x times 6, and then just use the double angle formula again. Oh, not related to the question you're doing? Gotcha. Medical Marvel, what was your question? What was your question? Cosine. You're asking if the simplification is correct. Sorry, what are you talking about? Medical Marvel, can you maybe hop on Discord and tell me what you're talking about? So like, if you're literally asking cosine squared divided by sine is equal to cotan times cosine, yeah, that's correct. If you're literally just asking about cosine squared divided by sine is equal to cotan times cosine, that is literally correct, right? Wait, someone else had a question about question 2, FB Addison, right? FB Addison was asking about question 2 in the York problem set, which basically just boils down to an uncareful use of multiplying through. Remember, they have some positive number of b, and they claim that g of x is less than or equal to b, right? This is a true statement just by the hypothesis. But then they try to multiply through by f of x times g of x, and they try to claim that this is less than or equal to f of x times b. And this is just, you can't do this, right? Because you have no guarantee that f of x is positive, right? Because instead, let's write this, in elementary school level, right? 1 is less than or equal to 2. If you multiplied through by a negative number, a number that's potentially negative, like let's say you multiplied through by like y, right? You wanted to claim that y is less than or equal to 2y. Well, if y is negative, this just isn't true. If y is negative, this just isn't true. And that's the issue here. You just have no guarantee about the sign of f of x. I just want you to think that through a little bit. Could you do cosine squared of 3x is equal to 2 cosine 6x? Swan? Yeah. So that's just Yuli the Muli. Yeah, you totally could, right? That's using the double angle formula for cosine rather than the double angle formula for sine, but it's pretty much the exact same idea, I think. Right? You can use the identity for the left hand. Oh, Vulgar Desperado. I'm trying to remember who was who, but Vulgar Desperado was the one of the helpers from the math help subreddits, right? Was another helper who, I think you were like a PhD candidate for like engineering. Yes. Okay. I'm trying to remember all our friendly folks that help out all our wonderful students. Yeah. Okay. Okay. So let's get back. Okay. I hope the students working on the calculus 2 integrals had a nice break, because we're getting back to you right now. We're getting back to you right now and looking at some more difficult problems, right? So, okay, the double angle formulas is stuff that you really got to know, right? You should be making maybe make a list of your stuff off to the side, like of concepts to know. Do you remember that like Phoenix rising from the ashes integral where you had like I is equal to, something minus like, 1/16 I? Or let's just call this a constant, right? This is one of those constants. This is one of those ideas you should really know from, yeah, that term is so cool. This is one of those things you should really know from integration by parts, is that, well, the answer at this point just becomes I times 1 plus c is equal to like that something. So I is just equal to that something divided by 1 plus c, right? I think it was Yuli the Muli that told me that in their country this was called, Phoenix integrals, because you see a smaller integral rising from the ashes of the larger one, right? I think it's a great term. I always wished I had a name for that, and now I do, so I'm very thankful. But then other stuff is like the cosine and sine double angle formulas, right? I'm basically just creating this like sort of impromptu list of things that you should know. Double angle formulas. You should also know the identities, like cosine squared x plus sine squared of x is equal to 1. And you should know that tan squared of x plus 1 is equal to secant squared of x. I think there's also one with cosecant, but that one I always forget. This motherfucking wasp just landed on me. God damn it, get off. Get off. Jesus Christ. Sorry about that. Yeah, okay, so as we're creating, so now we're doing 22, right? Sorry, I get very agitated when bugs decide to just, land in my head. So this turns into sine of 6x dx, right? So, okay, what's a little nasty about this is that the powers aren't quite the same. So the double angle formula isn't really a good candidate for this one, right? The double angle formula is not a great candidate, I would say. But this one's an odd power. So let's use that trick that we were talking about earlier, where we split up in, because it's an odd, or specifically to the third power, let's split this up into sine squared. I guess is a 6x times sine of 6x times cosine squared of 6x, right? And then this is equal to, I'm going to try to use the 1 minus cosine squared formula here. So this is 1 minus cosine squared of 6x times sine of 6x dx, right? So if we multiply this through, this turns into cosine squared of 6x minus cosine to the 4th of 6x times sine of 6x, right? And this isn't so bad. This isn't so bad at all, because one of the integrals turns into cosine squared of 6x times sine 6x, and the other one turns into cosine to the 4th with sine. Right? And in either case, just let u be equal to cosine of 6x. And then du. So I'm just, writing it. It's two separate integrals that are done pretty much exactly the same u sub. This turns into minus 6 sine of 6x dx, right? So this just turns into an integral of u squared du, and this turns into some integral of u to the fourth du. And either way, it should be really easy. Either way, it should be really easy. Yeah, cosecant squared, that sounds about right. Cosecant squared is equal to 1 plus cotant squared. That sounds very believable to me. This one I don't use nearly as often as the rest, though. Because this one, the cotan and the tangent identity are used in almost exactly the same way, and I'm just more comfortable with the tangent identity. Just more comfortable with tangents than cotangents, right? Because the use case is almost exactly the same. When you see 1 plus some like x squared, you can convert that to either cotangent squared or a tangent squared. But how are we feeling, folks? To the folks following from the Calculus 2 course, are you feeling good right now? Are we still making good progress in understanding stuff? Because I'm happy to just keep going through a couple more problems from each variety. Probably don't have that much time to go through like literally every single one, but we can cover a good number of them. Right? We want to see the big thematic ones, right? So remember when I was saying that you definitely want to know the double angle formulas and whatnot? This is one of those where they shine, right? So what is it, like cosine 2x is equal to cosine squared of x minus sine squared of x is equal to, I think, 2 cosine squared of x minus 1 is equal to 1 minus 2 sine squared of x. Does that seem right? Does that seem right? 1 minus sine, 1 minus sine, right? Yeah. Can't go on all, but as long as we can get a gist in each lesson, it's okay. Yeah, exactly. Okay, sounds good. So what we want to do right now is, because eventually at some point it becomes repetitive, right? But that's not a bad thing. You can practice those extra problems on your own. But I'm trying to hit like coverage so that you see sort of every concept, right? And this is a problem that looked really hard for me until I remembered that, oh wait, double angle formulas exist. I had completely forgotten about their existence, just, you know, from the years of unuse. And this just makes everything super easy, right? Because this means that cosine of 2x plus 1 over 2 is equal to cosine squared of x, right? So this looks almost exactly like what you have over here, except it's x instead of 2x. So we just need to have it, right? So this means that if you just, because remember, you can, the cosine formula for x would also apply to x over 2. So what I'm telling you is x over 2, cosine x plus 1 over 2. This is a perfectly valid identity, right? So now we're just going to plug this bad boy in over there, and we're just going to reap all the profit. So this turns into cosine squared of x over 2, square root of that. And hey, the square root of cosine squared is marvelously, believe it or not, just cosine, right? And then this just turns into the integral of cosine x over 2 from negative pi to pi. Negative pi to pi. Yeah, looks like I got the cosine squared, double cosine angle formula just fine, just right. Yeah. Folks, does this make sense? This is a pretty big deal. You use the double sine and double cosine formulas quite a bit, and I think those are things that you pretty much got to know, you know, down cold, as they say. Are we good to move on, folks? Do you see what I've done there? Do you see what I've done? Java and Mad Max? Okay, cool. I get a little bit nervous because I think there's maybe 2 or 3 students from the class speaking for about 8 or 10 people, and I hope that everybody's following along. Like I said, if you want to be able to participate in the comments yourself and ask questions, just make a Twitch account. It's hopefully not too bad. It's hopefully not too bad. You should just be able to make one, you know, in 5 minutes or so, maybe even a minute. But yeah, this is almost the exact same. Wait, no, this one's so easy, right? 1 minus cosine squared is just the cosine squared identity. Cosine squared x plus sine squared x is equal to 1, right? By the way, how did they go from this various formats, right? So cosine 2x is equal to cosine squared x minus sine squared x. All they did was plug in that cosine squared of x is equal to 1 minus sine squared of x to get this one. And then they plugged in sine squared of x is equal to 1 minus cosine squared to get this one. So this is just like a reformatting. This is just a reformatting using this identity, right? So, okay, 1 minus cosine squared is equal to sine squared. So this just turns into sine of x dx. And you all know how to do this one at this point, right? It's whatevs. Well, I think it's, a big part of the value here is that almost any student can ask any question that they have in chat, right? Stop me if something doesn't make sense. I think that's a huge part of what makes this platform a little bit special. Couldn't find out how to use mic to speak in the stream. Oh, sure. No worries, Medical Marvel. I'm happy to help. Yeah. Okay. Well, I'm happy that the feedback is positive so far. And no need to refer to me as a sir. I'm 25 years old. I'm not that old yet. You can call people sir once they get a PhD or once they hit age 30, I think. And I'm not currently a grad student, so I think I've got at least 5 more years before you can start calling me an old man. Hopefully. Anyways, this problem is almost identical to this is almost identical, right? Earlier we did rad of 1 plus cosine x over 2. Now it's just rad of 1 plus cosine x. So I'm going to write out the identity again, right? Cosine of 2x is equal to, what is it, 2 cosine squared of x minus 1? Right, so this turns into 1 plus cosine of 2x is equal to 2 cosine squared of x. So this time we just don't divide through by 2, right? Don't divide through by 2. So this 1 plus cosine of 2x is equal to rad 2 times cosine of x. Okay, and instead of 2x and x, now we use x and x over 2. So x is equal to rad 2 cosine x over 2, right? Not so bad. Not so bad. So this just turns into the integral of rad 2 cosine of x over 2 dx from pi over 3 to pi over 2, right? Hopefully, this is, you're seeing the gist. A lot of these trig substitution problems, you just gotta, crunch them through, simplify them a little bit until you see something that you know how to do. Until you see something that you know how to do. Right, folks? How are we feeling about these trig sub problems so far? Scale of 0 to 10. 10 great, 0 horror. Horror. I hope none of you are, below a 5. Oh no, really? Okay, we just gotta keep crunching more of these problems. So some of the difficulty comes in from, oh my god, this what do you call it? Oh my goodness, this a double angle formula that I haven't seen in 2 years is rearing its ugly head. And I realized that, if you don't know it, it looks terrifying, but you just gotta make a big list of the things that you need to know, like the double angle formulas, the trig identities. And once you have them in your head, a lot of these problems are, after you try out like 2 or 3 different things, some very clear path pops out. Right, so, okay, sine cubed, cosine to the 5th. Right, so what do we want to do with this one right now? So as I was saying earlier, when you see like sine to the 3rd power, I think this is a really great cue to break this up into sine of x times 1 minus cosine squared of x. Right, and just cosine 5th of x dx, integral of 2. So, okay, let's put the 2 out in front of the integral. So this turns into sine x cosine 5th x minus sine x cosine to the 7th x. And again, we've seen this so many times, just like u is equal to cosine x here, and du is equal to minus sine x dx, right? So this turns into a, u to the 5th integral, and this over here turns into a u to the 7th integral. And the du takes care of the sine perfectly. Takes care of it perfectly. Devere was asking, hey, you just joined, but wondering if you answered the question from the Discord why all the terms are divided by theta to the... Yeah, I did. Like, it's not so mysterious, right? They're just taking a limit. That's just the way you want to write it if you're, like, going out of your way to take a limit. Like, if you had some term that just looked like this, right? You could eyeball it and just say, hey, the limit is 2, because you just compare the x to the 4th terms, the highest power terms. But if you wanted to do it a little bit more carefully, you would divide through everything by x to the fourth to be able to say that, okay, if you divided everything through by x to the fourth, this looks like the limit as 2 plus 1 over x plus 1 over x squared divided by 1 plus 1 over x squared plus cosine of x over x to the fourth, right? Dividing by x to the fourth just makes it super clear that all these terms die when x goes to infinity, and all that you're left with is 2 over 1. Right, that's all. I'm getting a surprising number of questions about that dividing by x to the fourth thing. Yeah, it's that one's just a limit. It's just a limit. Okay, so yeah, I think this answer is question 28 just fine. It's not so bad, right? It's just, you know, when you see sine cubed or cosine cubed, I think that's a really great opportunity to just use one of the cosine or sine squared identities. Because the reason this works is because when you split it up this way, the sine squared you can convert to 1 minus cosine squared, which is part of the other, you know, which combines nicely with this stuff. And then the sine of x works really nicely to give you sort of, you know, the repercussion of a chain rule. When you do go from cosine, u is equal to cosine means that you have to have a sine floating around. And the sine basically absorbs the impact of the chain rule, so to speak. You see what I'm saying? That's the sort of pattern recognition you need to be looking out for right now. Yeah, the sine just pops out. You know, when you have the sine alone, it's really, really good to use it as sort of your, what do you call it? Your extra wiggle room. It's sort of like your landing pad for your chain rule. I'll try to think of a more elegant analogy later. Right. It sort of is exactly what lets you, you know, it's what makes the chain rule work perfectly, these kinds of problems. So 29 is probably the easiest problem we've seen so far because it uses the same concept. Now it's so simple, we don't even need any substitution, right? Exact same idea. Cosine, u is equal to cosine x, du is equal to minus sine x dx, right? This just turns into an integral of u to the fourth. There's going to be some negative signs here and there that you got to be careful about, but you know what? Let's just do this problem out once, just this once, right? So this turns into du is equal to minus sine x dx. So this turns the minus du is equal to sine x dx, right? And cosine to the fourth. Okay, so this turns into u to the fourth du. You see why that is? The negative sign pops out front, and this just turns into a minus 1/5 u to the fifth, right? And then you plug it back in for u, this just turns into a minus 1/5 cosine of x to the fifth. And don't forget to add on your integration constant plus c, right? This is just sort of one of the simplest and most succinct examples of this pattern of going from cosine to sine or vice versa, right? When you have when cosine is at some high power and sine is on its own, that should be your immediate cue that u substitution is going to work. And vice versa is just as well. When sine is to some high power and cosine is by its own, it'll serve as a perfect landing strip. I don't know what the right term here is, right? It'll serve as the perfect complement or something. I don't know. Anyways, we keep moving on, right? We keep moving forwards. We need to get to some other ones that look like tan of x times secant to the fourth of x dx. Right? So what does this look like? Tangent of x, secant fourth x dx. Yeah, so this one had a really neat trick to it, I think. Ooh, did I not use that trick? Yeah, so initially I wanted to make u equal to tan x, and then du is equal to... Initially I tried doing it this way, u is equal to tan x, and du is equal to secant squared of x dx. But, you know, this wasn't working out so well, right? Because then you would plug this in and you get tan x is u, and then you would have an extra, you know, du is equal to, so this turns into secant squared dx. So du would be this part, but then you would have this extra secant squared of x lying around that you couldn't do anything with. So what I tried out was, okay, what if you do something like, I remember to myself, what's the derivative of secant, right? It's equal to, the derivative of secant is just equal to secant u tan u, right? So I thought to myself, this could be really promising, because this preserves the secant and sort of spits out an extra tan, right? So maybe if we let, sorry, I guess I should make this x's, right? X, 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 X. So my idea is maybe if we let some of these secants be u, and then we take the derivative, then we get a secant tan pop out beautifully. Is u is equal to cosine x still helpful, or maybe convert? Yeah, Uli the Muli. That's exactly the idea. U is equal to cosine. That's exactly what I'm saying, right? For a problem like this, right? Even though cosine is to the fourth power, u is equal to cosine x is exactly what you want, because when you take the derivative, the sign of x just pops out beautifully for the chain rule. From the chain rule, and it sort of soaks up the extra stuff. But the point for this problem is looking at, okay, secant of x. Well, the derivative is both secant x times tan x. So I decided to just start playing around with some terms, right? Let's try out u is equal to secant cubed of x. Then du is equal to 3 secant squared of x. And then by chain rule, you get secant x tan of x, right? It's like, darn, that almost works. That almost works. Right? But when we multiply this stuff together, like this is just one too many powers of secant, right? Because the idea is that we hopefully would get, replace everything. Sorry, the idea is that we'd like to replace everything here with u du, but the issue is that secant cubed, secant squared, secant to the first power, that's a total of 5 powers of secant, so that's one too many, right? That's one too many. So now I just said, okay, let's try the next thing. Let's try u is equal to secant squared of x. And what do you know? This turns into 2 secant x times secant x tan x, right? And this is 2 powers, this is 1 power, this is 1 power. It works out perfectly. You see what I'm saying? You see what I'm saying? Because at this point, so if du over 2 is equal to secant x squared times tan x, and u is just equal to secant squared, right? Look at our original problem. This means that tan x times secant to the fourth x is just equal to u du times a half. And it's perfect. It's really, really perfect. And then at this point, this is just a super standard integral, right? And then you would just have to plug in equals 1/4 secant squared of x squared. I think this is a definite integral, so you would have to evaluate it. Can you still do this? You have u is equal to secant cubed, so you could cube root of u is equal to secant. Actually, you're right. No, you're probably right. That would work just fine. Yeah, so you would just have to divide by a cube root of u, which I think that would work, right? So then if, cube root of u is equal to secant, then this just becomes like, it would become like u du over like cube root of u. Yeah, you could do it that way, but I think this way is a little bit cleaner, right? I think this way is a little bit cleaner. Yeah, that's a good suggestion. The thing about integration is just that there's so many ways to tackle a problem, right? Even within the same method, like u substitution, there's a couple different ways to make something work, typically. And one of my physics professors from college joked that you can teach a monkey to do everything that humans can do, except for integration, right? Integration is one of those things that sometimes requires a little bit of cleverness, or can't just be boiled down to a mechanical procedure like so many other things in mathematics can be, right? Now this is obviously a joke. Math gets really hard, but the idea is that at least in your like high school careers to early college careers so far, most of the stuff you did, if you just practiced it, could be like really, really mechanical to where you would guarantee yourself the answer every time. Integration, however, you could get in the past, you could guarantee, you would get your answer in the first try if you were practiced well enough. Integration, however, just requires a little bit of elbow grease and a little bit of trial and error. And sometimes multiple ways work out. And sometimes you're just banging your head against the wall because it feels like nothing you try works out. It's all over the place, folks. And you just got to get used to it. You just got to get better and better. How are we feeling? I think these trig problems are kind of tough. And a lot of them have some slightly different concepts. So I'm probably going to run through all the trig problems. The partial fractions and the trig substitution problems later aren't quite as bad, in my opinion. Like once you see the pattern, there's only like one or two patterns, whereas for these, there's a lot of different patterns. So let me just try to run through these. Yeah. Okay, so how did I do this one? Right? I think for this one, I just wrote it out and saw what it looked like. So cosecant, this is just equal to 2 integral of 1 over sine cubed of x. And cotan is cosine of x over sine of x. Right? Well, hang on. This is starting to look real nice too. Because remember what I said about the pattern of when sine was to some power and cosine of x was sort of on its own next to dx? Well, that works just fine, even if sine is on the bottom. Right? There's no reason why you can't do u substitution for this too. So if you let u is equal to sine of x and du is equal to cosine of x dx, what does this turn into? It turns into something super clean. Integral of 1 over u to the 4th du, right? And you all know how to do this. This is one of the elementary integrals. Not so bad, right? So I think the biggest thing to take away from this part is that try to look for ways to, have sine to some power and then cosine x dx, as your chain rule, as your output from the chain rule. Or I guess that's not even chain rule. It's just sort of your output from taking the derivative. Right? But 32, what is 32? So now 32 is asking about tan cubed of x times secant cubed of x dx. Oh boy, what is this? What is this? So what is this? This is sine cubed of x over cosine cubed of x. And this is 1 over cosine cubed of x dx. By the way, my hope is that this platform is a little bit more engaging than doing problems like totally on your own, right? I'm hoping that we can have a little bit of fun here and there. I try to break up the, a monotony sometimes with a terrible math joke here and there, a funny story from college. I got a handful of, stories from very wacky characters throughout my 4 years. Okay. Yeah, this one isn't so bad either, right? So this is a multiplication sign. So this looks intimidating because it's like, oh, darn, if only this was like sine to the first power, we would be done, right? If only this was sine to the first power. Well, let's try that out, shall we? Remember that breakdown I always suggested that you use, like sine times sine squared? So, sine cubed is equal to sine times sine squared, right? And sine squared is 1 minus cosine squared. Ah, well, if this is cosine 6x on the bottom, this starts to look very promising to us, right? This starts to look very promising. Ouch, my hand hurts. This just looks like sine x over cosine to the 6x minus sine x, and you get a little bit of cancellation here because cosine squared and cosine to the 6 cancel out to give you cosine to the 4th x. Right? Exact same pattern as before, just dressed up a little bit, right? Just dressed up a little bit. They call this reverse chain rule in German books. No cool name. Yeah, darn. But like, what's the opposite of a chain? Like a mace? I don't know. There has to be a better name for this method. It's used too often. Yeah. If only everything came with a cool name. I feel like there's just so much branding, right? Unchained. Oh, it's like Django Unchained. Integrals Unchained. Yeah, that's pretty cool. Yeah, I'm very much reminded of that Tarantino movie. Okay, sine squared of x cosine cubed of x dx. It does sound rad. Yeah, I would say just do exactly what we've been doing, right? my favorite way to do this is to split the cosine into two parts, cosine to the first and cosine squared, so that we get sine squared of x times, okay, so cosine squared goes here, 1 minus sine squared, times cosine of x dx, right? And at this point, we've seen so many examples. This turns into sine squared x cosine x minus sine to the fourth x cosine x, right? We've seen this so many times. Let sine of x be u, and you're golden. And you're golden, right? Not so bad. I hope when I say not so bad, it doesn't come off as condescending or anything. I genuinely mean that I feel like it shouldn't be too terrible. Okay, sine of 4x and cosine of 2x. So your problem, the fact that the arguments are different, 4x, as opposed to 2x, should be screaming at you to fix this, right? We got to try to make this, make the arguments. I don't know how to do anything with sines and cosines unless the arguments are basically, the same. So let's try to see if we can do something like this, yeah? Or, when they're being multiplied together, I need to fix this. So let's try using the double angle formula, right? Sine of 2x is equal to 2 cosine x sine x. So that means that that means that sine of 4x is equal to 2 cosine of 2x times sine of 2x, right? So, okay, let's just replace that. Cosine 2x, sine 2x, cosine 2x, dx. What do you know? Cosine 2x, sine of x. Yet again, this exact same pattern rears its head. Cosine 2x, sine of 2x, dx, right? We let u be equal to cosine of 2x, and that probably takes care of the entire problem for us. It's not so bad. Oh, by the way, I forgot to ping the all the group at large in Discord to let them know that I'm live. Let's see, stream live notification. That's everyone. Now for help. Yeah, after we get done with this last problem, we'll probably take another couple of minutes of break, right? Can we go the opposite way too? Use 1 minus cosine squared for the sine squared? Yeah, I think so. I think it's just a little bit nasty. I think it's a little nasty to handle a cosine to the... Yeah, so what would you have done? On 33? So if you had split this up, this would have turned into 1 minus cosine squared of x times cosine cubed of x, right? I think it's just a little bit annoying to integrate cosine cubed of x and cosine to the fifth x. I'm sure it can be done. But I really like having like an extra cosine lying around to soak up, to sort of like handle the chain rule, right? This makes it so much easier. With something like this, I'm sure it can be done. You would just have to come up with some other splitting. You might run around in a circle a little bit. Okay, so 35, right? I wouldn't say you're bad. I'm sure it can be done. I'm sure it can be done. Okay, so cosine of 6x, cosine of 4x. Okay. It's a little bit obnoxious because this uses some other rule. Yeah, u is equal to cosine cubed. Yeah, that might work. That could work. Yeah, okay. I see what you're saying, Yuli. You could probably get away with that. That would probably do the trick. Yeah, 35. I'll just have to tell you, this requires you to use a cosine addition rule. And I think it's unfortunate that the last problem, the homework set, requires bringing out some new piece of trig identity. But you just got to remind yourself that this is equal to 2 cosine a plus b over 2 times cosine a minus b over 2. Right? So the idea here is that we need to make a plus b over 2 and a minus b over 2 equal to 6x and 4x respectively. Right? So a plus b over 2 is equal to 6x. We're basically just solving for a and b to try to rewrite this in terms of a sum of cosines rather than a product of cosines. So a minus b over 2 is equal to 4x. And I won't do the workout. This is just some very simple middle school system of equations, right? But if I remember correctly, a is equal to 10x and b is equal to 2x. So this is just equal to, okay, so the half needs to come on the other side, right? So this is just equal to 1/2 times cosine of 10x plus cosine of 2x. And these are totally easy to integrate on their own, right? You just have to do different, you have to divide by 10 because of the chain rule over here and divide by 2 because of the chain rule over there, but not so bad, right? Not so bad. All right, folks, how are we feeling with these trig problems? How are you feeling with them? 0 to 10? Scale of 0 to 10? So far, not so bad. 5? Okay, all right. I guess a 5 is not technically terrible. A 9? Okay, good. Yeah, hopefully I work easily with the extra sign. Yeah. Okay. Do we want to take another 5-minute break? What do you all think? And what do your classmates think? I don't want to, marathon sessions are good for, compactness, but you also got to take a moment to just take a breather and get some water too, right? Are there practice sites for trig identities? I'm sure there's got to be, right? I just don't. I haven't really looked at resources for this in a couple of years. Yeah. 5 minutes does seem bad. I assume you meant to say doesn't seem bad. Class agree? All right, folks. Let's take another 5-minute break. Break. Back at, let's call it 7 p.m. EST. Okie dokie. And by the way, like I said, if there are other people you're aware of who might like help for this class, please let them know. Just generally speaking, I'd like to expand this from, students who are part of one class to, any student in that class that would also like help, but also don't forget your friends at different courses, different universities and whatnot. There's no one I'm not happy to teach. I'm like teaching a lot. I like math a lot. Anyone that you know who might like this idea, please share the link with them and, explain how it's helped you. But yeah, let's all get some water, take a break. All right, folks, I'm returned for using the restroom break. We'll probably just give it another minute for people to recover. And yeah. Hype. Okay. Funny. Yeah. I by the way, I'm very grateful that Jabba and all your classmates and friends gave this format a try. I've been doing this for about 3 weeks now, as sort of a hobby to reconnect with math a little bit. Um, I frequently felt like live instruction is still stuck in the Stone Age, and just sort of had this cool idea to, see if you can make a difference in some, students' math careers. I hope that you'll, spread the word of mouth around at your school, and let anyone who might need help come our way. Yeah. Actually, if you feel really good about the idea, we have some posters on the Discord. They're kind of amusing. We, tried to make them as eye-catching as possible. But I've been asking, if you like the idea, you can always consider putting up a one of those posters or flyers, at your local lecture hall or university or whatnot. But anyways, let's begin again. So we finished all the trig questions, and now we're going to look at trig substitutions. Oh boy. So these questions took me a moment. Spread the word. Okay, awesome. Yeah, I'm really grateful that, so what I've found is that a lot of students are just so skeptical of the idea of, someone, doing some tutoring, or doing, I guess it's more of a math help desk than a tutoring, sometimes I think. I don't know, still trying to find the right words. But, there's a ton of YouTube channels out there. Like Khan Academy revolutionized asynchronous teaching, right? But I still feel like synchronous or live teaching is stuck in the Stone Age. And I just think that there's a lot of value it could offer to a lot of students. But anyways, the identity here is, as before, tan squared of x plus 1 is equal to secant squared of x. Right? So what we're hoping to get is that, okay, so the first time we do this, let's write this out really carefully, right? To make it clear what we're doing. But if we write this out as like rad 9 times rad 1 plus x over 3 squared. You see why I did this? I just separated out the 9, right? If you put the 9 back in here, it would turn back into exactly the same thing. But the idea is that we want 1 plus x over 3 squared to look exactly like 1 plus tan. So I guess I'll call this maybe a u or something to not reuse the x. So I really want this to look like 1 plus tan squared of u, so that I can replace it with secant squared, right? And you see, I can do the reason I'm trying to do this is because instead of 1 plus tan squared, secant squared is just one term. And that square roots really, really nicely. You see what's happening? So this integral turns into, what I'm basically demanding is that x over 3 squared is equal to tan squared of u. So x over 3 is equal to just, was it tangent of u? Did I do this right? Yeah, I think it's fine. X over 3 is equal to tangent of u. So then dx over 3 is equal to secant squared of u du. Right? Right? Yeah. So if we just plug this all in, so what does this turn into? This turns into like a 9 over 3, which is just, 9 over rad 9, which is just 3. And then dx becomes times 3 secant squared of u du, divided by the square root of, well, the whole point was to get this to be secant squared, right? Okay, so this then turns into 9 secant squared u du over secant of u, which is just integral of 9 secant of u du. right? And again, secant was one of those slightly nasty ones. Secant was one of those slightly nasty ones. And I think you just got to go, you know, it's nasty, but it's also standard, right? You should be able to find it in your textbook. But this just ends up being equal to 9 ln of tan of x plus secant, or I guess, sorry, it's of u. Right? But we're not done because we need to plug this back in for x. And the way that you typically do that is I typically like to draw a little triangle here, right? So we said that tan of u was equal to x over 3. So you can think of u as basically an angle, right? So if u is the angle, the tan is x over 3. So the hypotenuse is x squared plus 3 squared, right? This is a right angle. Yeah? So then the tangent of u, again, is, okay, that's just x over 3. But, the reason I did this was so that we could find the secant, which is one of the cosines. So that turns into root x squared plus 3 squared over 3. Yeah? And then you have to add the c at the end. So yeah, that's what that looks like. So the first time you do a problem like this, it might feel a little bit overwhelming. I get it. But you just have to, every single one of these trig substitution problems follows like this incredibly narrow formula, right? Whenever you see a 9 plus x squared, or like, okay, so there's a couple different forms. It's like, if you see 1 minus x squared, that means you should probably turn this into, 1 minus sine squared is equal to cosine squared, right? If you see, okay, so instead of 1, I guess I'll just call it a c, right? Some constant c, because you can always remove the 9 out like we did in order to isolate the, in order to isolate the remainder. It's just going to be like x over 3 or something, right? But if you see c minus x squared, that's your hint to use this, identity. That's your hint to use the 1 minus sine squared identity. If you see like something like c plus x squared, that's your hint to use the 1 plus tan squared identity is equal to secant squared. And then I think if you see like x squared minus 1, right? That's also a hint to use the same identity, just write it the other way around. It just becomes secant squared minus 1 is equal to tan squared. Yeah, note that this is x squared minus 1 is a little bit different from like, I guess I'll call it a c. X squared minus c is a little bit different from c minus x squared if it's inside the radical, right? If it's inside the radical, you got to be careful. You got to, make sure you don't get a negative value. So what do I mean? What do I mean by that? If it's inside the radical, like here, right? If you see something that looks like 9 minus x squared, you got to use, you're going to want to use this one. But if you see something like x squared minus 9 in a radical, then you're going to want to use this one. It just corresponds better. You know what I mean? Yuli the Muli has a suggestion. You like to do c minus something squared, means you do something squared equals c sine squared. Yeah, I see what you're saying. Yuli the Muli is basically just showing you like a mnemonic to look at it, right? Yeah, that's how I typically like to do it because I think it's just, more effort. But, the way I'll do it next time is basically when I see 9 plus x squared, I'm basically going to just go right off the bat next time and say that I'm going to demand that x squared is equal to 9 tan u squared, right? Because then when you have this, you can plug that right in and you can see how it works beautifully. The reason I wrote it out like this, because I really wanted to explicitly show you how the 1 plus x over 3 squared format obeyed the 1 plus tan squared u format. But next time I'm going to do this sort of shortcut and just go directly from 9 plus x squared to 9 plus 9 tan squared. You see what I'm saying? Yeah, I think I know what you mean, Yuli. I'm basically substituting the entire thing. I think it's the same idea. Just the first time I wanted to write it out very explicitly, because I know that it's going to be confusing for students looking at it the first time. But okay, so then this is 1 plus 16 t squared dt, right? That was really messy. Okay, all right. So 1 plus something, again, this is probably going to look like 1 plus tan squared. So right now, I'm going to want to let 16t squared be equal to tan squared of u, right? So if we do this out, that means that 4t is equal to tan of u, or 4 dt is equal to secant squared of u du. Okay, now we just start plugging things in. So 4 dt looks like secant squared of u du, and you divide that by 1 plus tan squared of u. Well, hold on. 1 plus tan squared of u is just secant squared itself. So, oh my gosh, look at it. It's constant. Holy crap. Right, guys? So the integral of 1 over du becomes just u, right? And then you have to evaluate this because it's a definite integral. Or sorry, we switch u back to, excuse me. So what the heck is u, right? U, and then this becomes, the tangent of u is sort of like 4t to 1. Right, so u becomes just the arctan of 4t, the inverse of 4t. And this needs to be evaluated because it's definite integral, right? From -1 to 1. So I think that's just the arctan of 4 minus the arctan of -1. I think that's all that is. Oh, am I stupid? Yeah, I wrote my work out wrong. Integral of 1. Yeah, sorry, sorry, my notes were wrong, but this work should be fine. You see why it just turns into this arctan at the end? What was the domain of arctan? Good question. What is it like? Is it 0 to pi, or I think it's pi over 2 or something? No, sorry, the domain of arctan is as big as you want, right? Because a tangent can go from very small to very large, arbitrarily small to arbitrarily large. It's just the range of arctan, I think, is pretty small, right? The range of let's just look it up. I haven't looked at this in years. Domain of arctan. Or hell, let's just write arctan. Yeah, so here we go. Okay, let's try my hotkeys and see if this actually works. Did that do what I hope it did? No? Streamlabs. Yeah, so this is arctan, right? The domain, the range is as large as you want. The domain only goes from, what's the limit? Is it pi over 2? Clearly it's approaching something. Yeah, anyways. Anyways, that's the idea of this problem, right? Yeah, I'm still getting used to my Streamlabs setup, but hopefully the new layout, it looks a little bit more, I don't know if professional is the right word, but just pretty, right? I don't care about professional, I just want to look pretty. But it means I have to switch back and forth between my laptop and desktop sometimes, which is a bit of a pain. By x square root of 16x squared minus 36. Okay, folks, so now we're, what is this, a slightly different example? So now look at it, it's x squared minus something, right? So let's look at what this looks like the most. So tan squared u plus 1 equals secant squared. So yeah, I think this is going to look like secant squared of u minus 1 is equal to tan squared of u, right? So we're basically going to want to make excuse me. Ow, ouch, ouch, ouch. So the hope here is that, we're going to want 36 secant squared of u minus 36 to be equal to 36 tan squared of u. So we're going to want 36 secant squared of u to be equal to 16x squared. That's the equivalence we need here. So 16x squared is equal to 36 secant squared of u. So what does this turn into? This turns into 4 over 9, I think. X squared is equal to secant squared of u. So this turns into 2/3 x is equal to secant of u. So then, if you take the derivative, 2/3 dx is equal to secant x. And remember, the derivative of secant is secant tan. Excuse me, this should be a u. du, right? So yeah, we just got to start plugging that in, folks. So that looks like 3/2 of secant u tan u du divided by, well, hold on, x is just 3/2 secant, right? And then the square, finally, when we get to the square root, we get 6 secant of u. Right? Does this make sense? Because, oh, no, excuse me, this should be a tan, right? Because we wanted sorry, I'm having a brain fart right now. Yeah, we wanted 36 secant squared minus 36 to be equal to 36 tan squared. So then this should just be a 6 tan of u, right? So then, oh my god, it all cancels again, right? Secant tan cancels out. What do you know? 3/2, in fact, even cancels out. So what are we left with here? We're left with 1/6 du, the integral of 1/6 du, which is equal to 1/6 times u, right? And if we draw a triangle for us again, u is an angle, and it's saying that secant of u is 2x over 3. So that looks like 2x over 3 like that, right? So because we don't really have where we typically don't think of an arcsecant function, so, u is basically equal to 1/6 arc cosine of 3 over 2x. Yeah. You see what I'm getting at, folks? We'll do a couple more of these, but they're pretty much all identical from here on out. Like, the variety isn't huge. Sometimes you'll use the other substitution, like instead of using tan squared u. So this one is a little different in that we used the secant squared minus 1 converting to tan, rather than tan squared plus 1 converting to secant, right? But it's the same idea. Hopefully we'll find one of these that uses the sine squared plus cosine squared formula. But, at a certain point, they're all going to start to look exactly the same, which is hopefully an indication that you're getting more comfortable. Right, so if you look at 40, it turns into square root of x squared minus 9 divided by x dx. Okay, right? Nothing too mysterious. Just got to remind yourself which one to use, and I think it's tan squared of u is equal to secant squared minus 1. So then we want 9 tan squared of u is equal to 9 secant squared minus 9. So 9 secant squared is going to look like x squared, right? That's what we want to match up. So x squared is equal to 9 secant squared of u. X is equal to 3 secant of u. Dx is equal to 3 secant u tan of u. If we plug these in, this turns into, okay, so secant squared minus 9, so it turns into a tan. So this turns into a 3 tan of u. From the square root gives us that. Divided by x is 3 secant u. And then dx just gives us 3 secant, okay, I guess there's a du here. Secant u, tangent of u, du. So secant cancels out, and I think all you're left with here is integral of 3 tan squared. Does that seem right? Does that seem right? That's actually a little bit nasty. Let me double check my work. Yeah, it's a tan squared, all right. Not so bad, right? Tan squared actually isn't bad at all, because this just turns into 3 integral of, well, instead of tan squared, let's use the same identity, right? Secant squared minus 1. And, oh, what do you know? The integral of 1 isn't so bad, and the integral of secant squared is just a tan. Yeah, the integral of secant squared, if you just look it up, it's just tan. So this turns into something nice and simple, and you just got to substitute in for the u again. Again, look at the triangles if you need to, right? So if this is u, let's look at the definition of u. U is equal to x over 3 is equal to the secant of u. So that's basically saying this is x and this is 3. So this is x squared minus 9, I think. Right? So then this turns in tan of u becomes x squared minus 9 over 3. And u is just any of these, really. I'm just going to say the arc cosine of 3 over x, right? There's a lot of equivalent things that you can choose here. There's a lot of equivalent things. It's not a big deal. We getting the gist, folks? Looking all right? Yeah. Hopefully you should be seeing, like, I'm hoping that you'll get sick and tired of these problems before I do. Because, you know, they're all so freaking similar. What's really elegant about them is that there's so much cancellation, right? Like, you know, it's like the game was rigged from the start, right? Your professor's only going to ask you questions that are all nice and cooked up. You shouldn't see anything. You should never see anything that's too nasty, right? Oh my god, these are such a drag. And 40, 41. But, you know, the fact that they're a drag also means that they're not too bad. So what is this? Dx over 16x. I feel like we did this one already. Did we not do this one? I swear. This looks so 1636 looks familiar. I swear we just did this one. Yeah, so I already covered 40 because I somehow managed to... This was actually 41. What was before that? 39 is 4 over 1 plus 16t squared. Ugh, they're all getting mixed up in my head at this point. X squared, so this was... Yeah, so we already did 41. Yeah, they all look the same. Okay, so 42. Okay, so this one was actually, I believe... okay, so this one is actually a good one. Because it'll demonstrate to us the other, because instead of y squared minus 16, it's 16 minus y squared. So it's a hint that we need to use the cosine and sine formulas. So what is this, an x? No. My eyes are just getting all blurry now because they all look the same. 16 minus y squared to 3 halves dy, right? So if... Okay, so this is sine squared of u is equal to cosine squared of u minus 1. No, that's not right. It's 1 minus cosine squared of u. 1 minus the cosine squared of u, right? So we're hoping to get 16 sine squared of u is equal to 16 minus 16 cosine squared of u. Yeah? So if we just match it up, we're trying to hope that this is cosine 16 cosine squared of u. Y squared is equal to 16 cosine squared of u. Y is equal to 4 cosine of u. Some of us have to leave. Some of us in class have to leave at 8. Oh, okay. Yeah, sure. Okay. Ending at 8 is better. Yeah, I mean, okay. We'll make this the last problem, the trig subs, and we'll do a couple partial fractions, and that'll be all right. Hopefully that'll do the trick. Wow, you really have class that late? Like, is that normal? Dy is equal to... Hey, Madinsky. Good to see you again. Okay, so dy is equal to minus 4 sine u. And yeah, let's just quickly see what this looks like, right? This turns into 4 squared cosine of u squared. And dy is just minus 4 sine u du. And then 16 minus y squared is, now it's just sine squared, right? So that's sine squared of u to the 3 halves. So what does this turn into? This turns into, well, I guess it's really minus 4 cubed, right? I'm just sort of bunching them up. Cosine squared of u. And this turns into a sine cubed u on the bottom. And there's a sine over here, du. Oh my gosh, you get cancellation. What do we get? Minus integral of 4 cubed. The sine and this cancel out a little bit. So now we're just left with cotangent of u squared, du. Right? And as it turns out, this is a perfectly nice integral. I feel like I missed out some cancellation here that I could have gotten. Right, this should have been, perhaps it should have been 16, right? Yeah, it should have been 16. So then there's another 4 cubed on the bottom that cancels out here. So all you're left with is the integral of negative cotan squared of u, and this actually turns out to be a standard integral, believe it or not. Is it standard? Let me double check. Yeah, I believe it's considered a standard integral, and if it's, you know, if you really need to see it, it's like the minus integral of, I think, right, well, it's just cosine squared over sine squared, right? So this is 1 minus sine squared over sine squared. So then 1 over sine squared you can do something to. That's a cosecant squared, which just turns into a cotan. But just take my word for it that if you crunch this through, you would get something that looks like basically just, you would get an integral that just looks like cotan of u plus u, right? You would just cotan of u plus u. And then you would just plug this in to get, you know, again, I've drawn this many times, but so if this is u, y over 4 is cosine of u. So this is y, and this is 4. And this turns into 4 minus y squared, 4 squared minus y squared. So then cotan becomes just y over square root of 4 squared minus y squared, I think. And then you would just get like, you know, arc sine of 4 squared minus y squared over 4. And really, you could have written this a lot of ways. You could have written this as arc cosine of y over 4, arc tangent of 4y squared over y, 4 squared y squared. Yeah, you could have written a bunch of different ways, right? By the way, anyone that has other questions, feel free to ask. I'm happy to juggle stuff around. But one thing that I actually noticed about this problem that actually tripped me up for a little while was that instead of doing sine squared equals 1 minus cosine squared, we could have just as easily done cosine squared equals 1 minus sine squared, right? Because sine and cosine are pretty much symmetric in this trig identity. And what I noticed is that if you actually did this entire thing with y is equal to 4 sine of u instead of cosine u, you actually do get a pretty different looking term at the end, right? What I found was that if I did this via an online calculator, I ended up getting some like really weird thing that was like y over arc sine of y over 4. And what I found out was that it turns out that even though these look different, it's minus 8 sine y over 4, it turns out that it just differs by a constant, right? And if they differ by a constant, that basically just gets absorbed by the c over here. That's the idea. But yeah, this is an example of, you know, having to do a trig sub with sines and cosines instead. And I think that basically covers everything you need to see from trig subs. There's just a lot more problems that are all basically the exact same idea. And you can hash them out for practice as your need dictates, right? And I think the very last thing that we ought to maybe take a quick look at is just partial fractions, right? Are folks feeling okay about trig sub, right? It's a lot of hassle and a lot of, you know, dirty work, but hopefully the concept is at least crystal at this point, where you're always just looking for the right substitution to get rid of a radical or something like that, right? Or just getting, you know, some perfect, you know, instead of 1 plus tan squared, you're getting a secant squared that cancels out perfectly. You're always looking for some nice radicals or cancellations or something like that. Okay, folks, do I need to go over, or would you like me to go over just how to do partial fractions in the first place, even before we get to the integration? Because they included some of these problems just for partial fraction practice. Yeah. Okay. So, you know, you can maybe go on YouTube and look up like a quick 5-minute explanation, but here's my like quick 1-minute explanation. Is that when you have situations, partial fractions, we typically want to write in terms of linear terms. But when you have a linear term that's squared like this, right? you have to write this in terms of a times x plus 2 plus b times x plus 2 squared. And honestly, I don't really remember the justification for why it's like this. It's just how it is. But the idea is that, okay, if you were to think through multiplying, if you were to think through, you're trying to separate it into some nice individual terms with, very simple a's and b's, just constant a's and b's. The idea is that if you were to go back and put this all over a common fraction, this would look like a times x plus 2 plus b. You're basically matching the numerators, right? X plus 5 is equal to ax plus 2 plus b. So at this point, it's basically saying, okay, compare the x terms to each other. This is like saying, the coefficient in front of the x is just 1, and that's got to be equal to a over here, right? Because this is the only term this is the only coefficient for x. So then for, the constant terms, we're getting that 5 has got to be equal to 2a plus b. So then b has got to be equal to 3. So this is equal to 1 over x plus 2 plus 3 over x plus 2 squared, right? And it's just slightly more difficult. Okay, what do they give us? 5 plus 2 over y squared, y plus 1, right? A times, it always comes down to solving some like pretty simple system of equations. And, it's something that you should have learned by middle or high school. It's something that I actually completely managed to forget that I knew. But, once you refresh it, it should only take a couple of minutes to get the idea back, right? So the reason you just got to write, the y and the y squared as separate terms out. I forget exactly why, but it's just something that's got to be done. You can look up the general format to solve these questions. But yeah, every single time it's like, okay, you put this under a common denominator. So this would have to be a y squared plus b times, okay, so b needs a factor of y plus 1 and a factor of y. And then d needs a factor of just y plus 1, right? And you just have to compare this to y plus 2. And well, that's the idea. Every single time, you basically just get 3 unknowns and 3 systems of equations, and you can always just solve for that, right? And what I ended up getting was that a was equal to 1, b was equal to -1, and d was equal to 2, right? This shouldn't be too bad, I hope. You should be able to just always, you should always just be able to refresh yourself and look online. I'm sure there's a billion YouTube videos out there that are how to do partial fraction decomposition. But the reason that they bring this up in the integral chapter was because that we use this all the time in integrals. Okay, so wait, hold on. Before we get to there, 53 is a little bit special in that t squared minus 9t minus 12 divided by t to the 4th plus 3t squared. This one's a little bit special because the order of the lead polynomials actually are the same. And I believe when that's the case, you have got to simplify it a little bit first. Right? Like this is called an improper. This is called an improper partial fraction because the lead term is too large. And when that's the case, you can always just separate it out first, right? So this turns into like t to the 4 over t to the 4 plus 3t squared, which just turns into t squared over t squared, and then t squared plus 3. So this cancels out, and this is just a 1, right? And then after this, you have to do, then after that, you do all the other terms. That's, a over t squared plus 3 plus b over t plus c over t squared or something like that, right? When doing partial fractions, you should also look up how to do this. Excuse me. This should have been something that looks like, because this is a nonlinear term on the bottom, this has got to look like at plus b, right? So this is something that you should all know how to do if, you went through high school, but it's something that I find is very easy to forget. So just look up how to do it, right? But the whole premise for why they want to do these partial fractions is that, if you have something really nasty to integrate like this, it's not clear how to do it. But if you break it up into these individual terms first, then it becomes a lot easier, right? It becomes so much easier to integrate when you can just break it up first. So we'll just do some very simple examples, right? So if, like, we have 3x plus 17, x squared plus 9x plus 20, right? Well, this just turns into an x plus 4 and an x plus 5 on the bottom. That's 3x plus 17. So then we're basically trying to express this in terms of, in ax, in a over x plus 4, and a b over x plus 5, right? And the idea here is that a times x plus 5 plus b times x plus 4 has got to be equal to 3x plus 17, just like the other examples we did, right? And this is not too bad. You just, again, you match up the terms with x, and then you match up the constants. And I end up solving and getting that this is equal to, a is equal to 5 and b is equal to minus 2, right? I'll let you do the work out on your own. So then this is equal to 5 over x plus 4 minus 2 over x plus 5, right? And this is just a very simple integral. This just turns into a what? Natural log. You should know how to integrate each of these terms individually. But say a natural log of x plus 4 minus 2 times natural log of x plus 5, right? And then you add a c into the end. But that's the idea here. It should be very simple because you take something that's very hard to integrate at first, and if you could just split it up into linear terms or simpler stuff, then integration becomes very easy. That's the big idea, folks. And, with that, I think that's probably all there is to say about the partial fraction integration. It's just all of them are pretty much the same. They're very similar. You asked a question about differentiation in a piecewise function. Yeah, let's take a look at it. Okay. So Yuli them only posted some Trig sub stuff. Looks great. Okay, folks. Well, yeah, I think